In Lesson 3, we're going to learn about the cast rule. This is probably one of the most important lessons in grade 11 math because it's a concept that you'll be using again next year. Because of that, we're going to break it into two parts. The goal for today will be to learn how to draw an angle in something called standard form, and to do so, we will learn some new terminology. We can draw any angle theta in a Cartesian coordinate system, and the process will be described below. For starters, we draw a line called the initial arm, and this is just a line that begins at the origin and is oriented along the positive x-axis. This can be seen in the picture to the right. I'll just highlight it. So that arrow I highlighted is your initial arm. This line stays fixed. Then we draw a second line called the terminal arm. One end of it is fixed at the origin, and that line is free to rotate. I'll highlight the terminal arm in the picture to the right. As we'll see soon, the terminal arm is free to rotate either clockwise or counterclockwise to put it in any quadrant of the Cartesian coordinate system. The end that is fixed at the origin is called the vertex. Please don't confuse this with the vertex of a parabola. And finally, the angle is measured between the initial and the terminal arms. This can be seen in the picture to the right. And this is how we draw an angle in a Cartesian coordinate system. When an angle is drawn this way, we say that it's in standard form. Please don't confuse this again with parabolas. And that's a lot of new terminology to begin this lesson. So please make sure you're familiar with them, as I'll be using them throughout lessons 3 and 4. And moving on, we recognize that an angle in standard form can be either positive or negative. By convention, positive angles are formed whenever we rotate the terminal arm counterclockwise relative to the initial arm. Let me explain in the picture to the right. Imagine we have our initial arm along the positive x-axis. I'll just draw it here for clarity. The initial arm will always be along the positive x-axis. Oftentimes it won't be drawn, just so that we don't clutter the diagram, but I'll make it clear over here. And imagine if the initial arm stays fixed, and relative to that, you rotate this other line called the terminal arm. And I'll just make that a little more clear in the picture to the right. Because we rotated counterclockwise, by convention, this is a positive angle. So just to remind you, counterclockwise is this way. In a similar way, a negative angle is defined when we rotate the terminal arm clockwise relative to the initial arm. You can see this in the picture to the right. So once again, please imagine we start with an initial arm on the positive x-axis. Imagine then that you take a terminal arm and rotate it some angle clockwise. If that was the case, we have a negative angle. And just to remind you, clockwise rotation looks like this. Just to make an analogy here, It's just like how you learned when you move to the right along the x-axis, that's the positive direction. And when you move to the left along the x-axis, that's the negative direction. That was a convention for the x-axis. This is a new convention for angle rotations. As you know, we can divide the xy plane into 4 quadrants. Imagine that theta is a positive angle. Then here is a rule that tells us where to find the terminal arm. Anytime the angle is between 0 and 90 degrees, you're guaranteed to find your terminal arm somewhere in quadrant 1. Similarly, if theta is between 90 and 180 degrees, then you're guaranteed to find the terminal arm somewhere in quadrant 2. If your angle is between 180 and 270 degrees, we're guaranteed to find the terminal arm somewhere in quadrant 3. And finally, if your angle is somewhere between 270 and 360 degrees, we're guaranteed to find the terminal arm somewhere in quadrant 4. So let's try and make sense of this convention. For starters, remember our initial arm is always along the positive x-axis. I'll just draw it again here for clarity, and I'm not going to label it just not to clutter the diagram. Because that's the location of our initial arm, we define this for convenience to be 0 degrees. And now imagine if you rotate 90 degrees counterclockwise, you're going to have a 90-degree angle here. So again, I'm rotating 90 degrees counterclockwise like that. We're going to end up where the y-axis is. And that's why we label the top of the y-axis as 90 degrees. If you keep rotating counterclockwise, you're going to eventually get to the negative x-axis. I'm sure you can imagine if you go another 90 degrees counterclockwise, we'll eventually get to the negative x-axis. That would be a full 180-degree rotation. And we can continue this. From 180, continue rotating counterclockwise. From 180, continue rotating counterclockwise. If you go another 90 degrees counterclockwise, you'll end up on the negative y-axis, which is why we've labeled this as 270 degrees. And finally, continuing to rotate in the counterclockwise direction, you'll eventually have completed a full circle. Going another 90 degrees will bring us to a full 360, and we're back to where we started. That's why we say the positive x-axis is 0 degrees or 360 degrees. So I hope that made sense. What we're doing is taking this arrow called the initial arm. I'll label it now. And we rotate that through some counterclockwise angle, and that produces our terminal arm. For those of you who took physics, it's almost like an initial and final position thing. Think of displacement, which is your final position minus your initial position. In a similar way, the initial arm is like the starting position and the terminal arm is like the final position. Except rather than distance, we're dealing with rotations. So with that being said, I have to define 3 angles for you, and they are the principal angle, the related acute angle, and the coterminal angle. So once again, this lesson is very heavy on terminology. Hang in there, but we need it to finish up the rest of the unit. Let's get started with the principal angle. This is defined to be an angle between 0 and 360 degrees. By convention, it is a positive or counterclockwise angle. We will represent it using theta. So please assume whenever you see the Greek letter theta, it's a principal angle. Here are some examples below. In the first image, we have a principal angle of 45 degrees, and I'm sure you can see why. Imagine that from the initial arm, which I'll sketch below. Remember, we often don't draw the initial arm just not to clutter the diagram, but it is there, and you're more than welcome to draw it. Actually, let me do that in the remaining images before we move on. I won't label every single one though, just not to clutter the diagram. But if you rotate that initial arm through a counterclockwise angle of 45 degrees, you'll end up somewhere where the red line is. So that would be your terminal arm. And by convention, we've rotated 45 degrees counterclockwise. That would be the principal angle. This is what a 90-degree principal angle would look like. It's counterclockwise rotation by 90 degrees. And finally, you can imagine rotating counterclockwise by 225 degrees, which will place you somewhere over here. Okay, so that's the principal angle. The next one we have to learn is called the related acute angle. This one can be a little more confusing at first. This is defined to be the angle between the terminal arm and the x-axis, but only when the terminal arm is somewhere in quadrants 2, 3, or 4. We denote it by the symbol beta. So that's the Greek letter beta. I'll just spell it out, B-E-T-A. As the name suggests, the related acute angle is an acute angle, so therefore it's somewhere between 0 and 90 degrees. Every principal angle has its own related acute angle. The only exception is when the principal angle is in the first quadrant. If that's the case, the related acute angle is equivalent to the principal angle. Let's take a look at some examples. So in each of the images below, the blue arrows are going to represent terminal arms. I'll just label the first one. And our initial arm is on the positive x-axis. So notice in the first diagram, the terminal arm is in quadrant 1. I'll also label the quadrants. So it's quadrant 1, quadrant 2, quadrant 3, and quadrant 4. Because the terminal arm is in quadrant 1, the related acute angle is the angle between the terminal arm and the x-axis. And you can see in this case, both the principal angle, theta, and the related acute angle, beta, are the exact same thing. However, in the second picture, notice that our terminal arm is in quadrant 2. So here's your principal angle, which I'm labeling as theta. But by definition, the related acute angle is the angle between the terminal arm, which I'll highlight here, and the x-axis, which I'll highlight here. You take the acute angle, the one less than 90 degrees. So convince yourself that that's why we label the following angle as the related acute angle. In the third image, our terminal arm ended up in quadrant 3. Here's our principal angle, but the related acute angle is just the angle between the x-axis and the terminal arm. So I'm trying to make this a little more clear. This angle right here is your related acute angle. And finally, if we're in quadrant 4, the related acute angle is the angle between the x-axis and the terminal arm right here. In this last image, notice that the principal angle theta is shown as a clockwise angle. What I'd like you to do, please, is draw it as a counterclockwise angle, which I'll do over here. Kindly ignore that for now, but we will come back to some examples like that later where you can actually rotate clockwise, but to be consistent with the definition, the principal angle has to be between 0 and 360 degrees. And it is a positive counterclockwise angle. And the last definition for today is what's called a coterminal angle. So coterminal angles are two angles that have the same terminal arm, but they're different in size by a multiple of 360 degrees. Let's look at an example. Consider the principal angles of 43 degrees and 403 degrees, which is really just 360 plus 43. If you look at the picture to the right, consider a principal angle of 43 degrees. So you take your terminal arm, rotate it counterclockwise by 43 degrees, and you're going to get this angle shown here. But what if you decided to rotate that terminal arm by 403 degrees? Well, if you rotate a full 360, you're going to end up back on the positive x-axis. Remember, a full 360 brings you back to where you started. And if you go an additional 43 degrees counterclockwise, you've rotated a total of 403 degrees, but then your terminal arm will overlap with the one that was only rotated 43 degrees counterclockwise. So because these two principal angles give us the same terminal arm, we call them coterminal angles. Please keep in mind that there are infinitely many coterminal angles. For example, let's take 43 degrees and add two multiples of 360. Okay, 43 plus 360 plus 360 will give you 763 degrees. We would say then that 43 degrees and 763 are coterminal angles. And this is because they're different in size by a multiple of 360. You can imagine that you can keep adding 360 again and again and again an infinite number of times. So in theory, you'll have an infinite number of these coterminal angles. But what I'd like you to really take away here in summary is that every time you rotate by 360 degrees, you get back to where you started, and this occurs forever. Let's look at a few special cases now. To begin, let's label the picture to the right. So we start with 0 degrees here, and then going counterclockwise, we have 90 at the top, 180 to the left, 270 at the bottom, and completing the circle, 360 as well. If theta is 0, then we haven't gone anywhere, so our terminal arm lies on the positive x-axis. In this case, the terminal arm would be coincident with the initial arm. If you have a principal angle of 90 degrees, then your terminal arm lies on the positive y-axis. If you have a principal angle of 180, then your terminal arm lies on the negative x-axis. Similarly, 270 degrees would result in your terminal arm lying on the negative y-axis. And then a full 360 degrees rotation would result in the terminal arm lying back on the positive x-axis. So remember, we're rotating here counterclockwise. And that completes the lesson. Let's put this to practice though. So I know there was a lot of terminology today, but you'll see why we needed to learn this. What we're going to do in example 1, and there's really just one example here with variations, we're going to sketch each of the angles below. We're going to sketch them in their standard position. So sorry, I'm using a slightly different term over here. I'm saying standard position. It's the same thing as standard form. We're going to sketch each of the angles below in their standard position or standard form and determine, if possible, the related acute angle. We'll begin with positive 30 degrees. So for each of these problems, I'd like you to please label your diagram first. If you'd like, you can also label the initial arm. You certainly, again, like I said, don't have to do this. But I'll at least do it for the first one just to make it clear. And now we rotate that initial arm counterclockwise according to what the principal angle is. In this case, it's 30 degrees. Now, you don't have to use a protractor for this. I'm happy if you just make a sketch. But rotating 30 degrees counterclockwise will probably put us somewhere here. Okay, so that's your terminal arm. And to complete it, we should label this. And there you go, done. Because we're in quadrant 1, the related acute angle beta is just 30 degrees. Remember, that's the angle between the x-axis and the terminal arm. Let's try another one. All right, let's begin by labeling the diagram. Okay, at this point onward, you don't have to draw the initial arm anymore. Remember, that's the arrow that starts on the positive x-axis. Just in the interest of not cluttering the diagram, I won't, and we'll just go ahead and sketch the terminal arm. So we get that by rotating 150 degrees counterclockwise. That's going to place us somewhere in quadrant 2. Once again, I don't need you to use a protractor, just a sketch is fine. And that'll place us somewhere there. You do have to label your angles though. So here we have theta equal to 150 degrees. That's our principal angle. And because we're in quadrant 2, we do have a related acute angle. Remember, we used the Greek letter beta for that. And that's just the angle between the x-axis and the terminal arm. In this case, I hope you can see it's 30 degrees. If you're not sure how I got that, beta can be found by taking 180 degrees and subtracting the principal angle of 150, which gives you 30 degrees. You don't have to show your work like I just did. Oftentimes you're probably fine to just see it and label it, but if you need to show a little work, that's fine. Okay, part C. And you'll see why labeling is actually very helpful. In this case, we have a principal angle of 290 degrees. So you know it has to be larger than 270. That's definitely going to place us in quadrant 4. So we're about an extra 20 degrees counterclockwise of 270, so roughly here. Please label the principal angle, just like that. And remember, the related acute angle is the angle between the x-axis and the terminal arm. So in this case, what's the angle that's left over? Hopefully you can see that it's 70 degrees, but if you don't be afraid to show a little work. So beta would be 360 take away 290, which gives you 70. To find the related acute angle, you kind of have to see it. So what I mean is we're in quadrant 4. Notice that we went past the 270. So we're definitely larger than 270, but we haven't passed the 360 yet. So we take the largest of one of those special case angles and subtract the principal angle. Usually that works fine. All right, so let's label again. All right, 330 degrees. So we haven't gone a full 360, but definitely larger than 270 again. So once again, we're in quadrant 4. It'll probably be roughly here. A sketch is fine. Label your principal angle, please. And the related acute angle would be this one right here. I hope you can see that it must be 30 degrees. And I'll show you the work again. We take 360, subtract our principal angle of 330, and that leaves us with 30. All right, I mentioned this earlier in the video. Now we have a negative principal angle. So whenever you see a negative angle, that just means to rotate clockwise. Let's begin by labeling the picture. All right, so from the initial arm, rotate 45 degrees clockwise. That would be this way. That's going to actually place us in quadrant 4, so roughly here. Now there's two ways to express this. I guess it's not wrong if you label this as a negative clockwise angle. But it's proper convention to label this as a positive counterclockwise angle. So let's try to stick with that and ask ourselves, how far did we have to rotate counterclockwise to get to this location? Well, instead of going 45 degrees clockwise, you can just go 360 minus 45 counterclockwise. And that's equivalent to positive 315 degrees. Try to convince yourself that they're really the same thing, but that's going to leave us with a related acute angle, beta, of 45 degrees. All right, next up, 390. So let's label the picture. So because we have 390, we would have gone past the 360. So we rotate a full 360 degrees counterclockwise plus whatever's left over. In this case, the leftover is 30 degrees. So it's like you're sketching an angle with a principal angle of 30 degrees. But we do have to show that we've rotated 390. So here's how you do that. You make a full loop and extend it kind of like a spiral to where you end up. And just label it as so. And that's how you label the principal angle when it's larger than 360. In this case, the related acute angle, again, is the angle between the x-axis and the terminal arm. This would be 30 degrees. And in part G, it looks like we have a repeat over here. So I'm just going to make one up on the fly. Let's maybe do, how about negative 180? Okay, here we go. So we have to rotate 180 degrees clockwise. That means starting at your initial arm, rotate 180 clockwise, and that's going to put you on the negative x-axis. So I'll get rid of this just to clean up the picture, but we will end up somewhere over here. And notice going 180 degrees clockwise is the same thing as going 180 counterclockwise. What about the related acute angle? Well, because we ended up on the negative x-axis, there is no angle between the terminal arm and the negative x-axis. So you could say a couple of things. You could either say beta equals 0, or you could just say that it doesn't exist. All right, and that wraps up part 1 of the CAST rule. I left you with a worksheet to get some practice. Please try that. This lesson was probably heavy in terms of new terminology. Please again do make sure you're familiar with it, as we will use it again in the next lesson, and it definitely makes an appearance again in grade 12. So with that, everyone, thank you very much, and I'll see you in the next one.